Okay, so we've now talked generally about probability, various ways of representing our probability experiments, be they tree diagrams, probability tables, Venn diagrams. We've talked about the concepts of conditional and independent, conditional probability and with that independent events. And so we've got that general probability. In the previous video, we had a look at discrete random variables, how a discrete random variable is defined, what it is, how you set one up, how you use it to calculate probabilities. And we also talked about some important ideas around the mean of a probability distribution, which we call the expectation or the expected value of the distribution, and the median to some extent, and we also talked about variance and standard deviation. And those ideas are going to still be important as we now look at the binomial probability distribution. So this is a specific example of a discrete distribution. Okay, so the things we looked at in the previous video are still going to apply here. We have some other sort of techniques we can use with these particular kinds of problems. In particular, the CAS allows us to deal specifically with a binomial distribution. We'll talk more about use of the CAS in the next video. But what we want to do here is set things up and give you an understanding of what the binomial probability distribution is. So if we have a probability experiment that results in a Bernoulli sequence. So a Bernoulli sequence is a sequence of probability trials for which each trial results in one of two outcomes. Okay, now it doesn't have to be success or failure, but you can define the two outcomes as being success or failure, or the outcome of interest versus the outcomes that are not of interest. So it doesn't mean that you have to this is where it's all about how you set up the problem. So it doesn't mean that the experiment has to have only two possible outcomes. It just means you need to define it in a way that there's only two things you're interested in, or one thing you're interested in and one thing you're not interested in. So for example, it could still be about rolling a fair die, where there is 6 possible outcomes. But if you set up the random variable so that what you're interested in is rolling a 6, then the two possible outcomes at every roll are that you either rolled a 6 or you didn't roll a 6. Okay, so it's all about how you kind of reframe the problem and how you think about it. You can often set up the problem to have two outcomes, the outcome that you're interested in seeing, and then everything else. The probability of, in a Bernoulli sequence, so two outcomes at each stage is what's important. The probability of success, which we use the letter P to denote, is constant for all trials. Okay, so rolling a dice is a good example. If I'm interested in rolling a 6, my success and failure are either I roll a 6 or I don't roll a 6. The probability of rolling a 6 at every trial is the same. It remains 1/6 every time. Okay, so that's important. If the probability changes from trial to trial, then you don't have a Bernoulli sequence and you won't therefore have a binomial probability distribution. Probability of failure, we sometimes use the letter Q to represent that, but Q is simply 1 minus P, so we don't really need an extra letter, but you might see the letter Q sometimes, referring to the probability of failure. And the third condition is that the trials must be independent. So therefore the probability at each stage is not of, for example, rolling a 6 at each trial is not affected by whether or not you rolled a 6 at the previous trial. So independent trials, constant probability for each trial, and at each outcome success or failure. And if that's the situation that you have in your experiment or your probability trials, then you have what we call a Bernoulli sequence. Bernoulli was a mathematician, and a Bernoulli sequence, if we set up the probability distribution, results in something called a binomial probability distribution. So the bi is to do with the two outcomes at each stage, success or failure at each point. Okay, let's start to have a look at this. So let's consider a situation with 3 trials. Okay, I'm just going to have success or failure at each trial. So my first trial, it's I either get success or failure. Probability of success is P, probability of failure is 1 minus P. At the next stage, having got a success in the first trial, I can then either get a success or failure. Probability remains constant at each stage, so it's still going to be P. Probability of failure is still 1 minus P. Okay. And then again, having failed at the first trial, I could have a success or failure at the next trial. Probabilities still remain the same. And we can continue that to the third trial. And from here, we're now getting the picture of the 8 possible combinations of success and failures we could get across those 3 trials. So we know we could get success, 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 success. success, success, failure, success, failure, success, etc. Okay. All right, so we've set up our tree diagram. So now let's work out some probabilities from that tree diagram using what we know about probability. So probability of getting 3 successes. Okay, so we can see that 3 successes, there's only one branch that connects to 3 successes. That's that branch there. And the probability of getting 3 successes is going to be p cubed. P times P times P. That's nice and easy. Okay, then what about if we could just get 2 successes? Okay, so 2 successes, we could go down this branch, success, success, failure. We could go along this branch, success, failure, success. Or we could have failure, success, success. So there's 3 different branches that are going to be relevant to having 2 successes. Okay. Now, what we notice here is because of the condition in the Bernoulli sequence that the probability remains constant, is that each of these branches is going to be the same probability calculation. So if we look at that first branch, success, success, failure, that would be P times 1 minus P. Okay. Which we could just write as P squared times 1 minus P. The second branch is P times 1 minus P times P. So that's the same probability. It's still P squared times 1 minus P. And the same down here, the probability here is 1 minus P times P times P. Again, it's still P squared times 1 minus P. So what we actually recognise is it's the same probability calculation, but then we're going to add them up. So what we actually have here for 2 successes is 3 lots of P squared times 1 minus P. Okay, let's think about looking at having 1 success. So 1 success, sorry, my pen stopped working for a minute. There we go. 1 success would be, let me get rid of those. Let's have a look at the branches that are about 1 success. So we could get success and then failure, failure. We could get failure, success, and then failure. Or we could get failure, failure, and then the 1 success. So again, there's going to be 3 ways that that can happen. Okay. And each of those probabilities is going to be the same again. This time it's P times 1 minus P times 1 minus P. Whatever order they're in, there's still 2, we're multiplying by 1 minus P twice, so we're squaring 1 minus P, and then we're multiplying by P. So it's going to be P times 1 minus P squared. And there's 3 different ways that can happen, so there's going to be 3 lots of that probability. Okay. And then finally, looking at getting no successes. Okay. So that is going to be 1 minus P times 1 minus P times 1 minus P, so 1 minus P cubed. And there's only one way that happens, just the one branch. Okay, so what we've essentially got there is a probability distribution. We've got a situation where, and this is it's a discrete probability distribution. So if we had X was the number of successes, then we could set up this probability distribution. It's got 4 possible, so number of successes in 3 trials. Okay, it's therefore got 4 possibilities. We could get no successes, 1, 2, or 3 successes. So they're the values of X. The probability that X is equal to X is going to be each of these 3 probabilities we've just calculated. So no successes is 1 minus P cubed. 1 success is 3 times P times 1 minus P squared. 2 successes is 3 times P squared times 1 minus P. And 3 successes is P cubed. So it's an example of a discrete probability distribution. We don't normally set it up in that way, but I want to be clear about that's what's happening. Okay, so let's now think about extending the logic of this. Okay, so these make sense. Okay, we've got 2 successes, so 2 branches with probability of P, 1 failure. If you're doing 3 trials, you can't just have 2 successes. You must have also had 1 failure because you've got to do 3 trials. And there are 3 ways of doing that. Okay, this is 3 ways of doing it. 1 success, so probability of success to the power of 1, and 2 failures. Okay, so probability of failure to the power of 2. This is just 1 way of doing it, and there are 3 successes. We could also extend this, like if we follow the same logic, we could say there's 1 way of doing it, we have no successes, and we have 3 failures, which essentially just gives us 1 minus P cubed. If we were to follow that same pattern, same logic up here in the top one. There's 1 way of doing it, we have 3 successes and no failures, and so we just get P cubed. Okay, so we want to kind of see that pattern. So let's sort of extend that out. So what about if we wanted to know about the probability of getting 5 successes in 8 trials? So probability of 5 successes in 8 trials. Okay, so let's think about that. We're going to do 8 trials. If we want 5 successes, we must have got 3 failures as well. So it's going to be the probability of success to the power of 5 times the probability of failure to the power of 3. Okay, so we have to have had 8 trials, 3 of them are going to be failures and 5 of them are going to be successes. The challenging bit is what goes here. So how many different ways are there to get 5 successes in 8 trials? So, you know, for example, one combination would be to get success, that's complicated, 5 successes and then 3 failures. But you could then have 4 successes, your failure, 1 failure, another success, and 2 failures. So the question is how many different combinations can we have? And that's what we need to think about here. So what it actually is, and so what I'm looking at here is, you know, essentially how do we work out what this number out the front here is? Now we don't want to have to draw a tree diagram. Okay, if we can solve the problem using a tree diagram, we probably wouldn't bother with the binomial distribution. We just draw a simple tree diagram if it's only got 2 or 3 stages. However, we're going to have 8 trials here. It would have 8 stages. It is therefore going to have, you know, 2 to the power of 8 different possibilities. Okay, so that's a lot of possibilities. 2 to the power of 8 is 256 different branches. So I'm not going to draw that tree diagram. So what we want to be able to think about is, in 8 trials, 5 of them need to be successful. How many different combinations are there so that I can have 5 successes out of 8 possible trials? And this comes back to our combinatorics, which you might remember having studied in Year 11. So the way that we can look at that is we've got 8 different positions. How many different arrangements would have, or how many different selections would have 5 of those 8 things as successes? And the way that we would calculate that would be to do 8. I've got 8 positions from which I want to choose 5 of them to be successes. Okay, 8 choose 5. So actually, this 3 up here, if you extend the same logic back to this example, that is, I did 3 trials and I wanted 2 of them to be successes. 3 choose 2 is actually 3. I'll talk about this a bit later on, but in your CAS menu, 5 for probability, 3 for combinations, gives us our NCR. And if we do 3, 2, there are 3 different ways of that happening. If we have a look at this example here, 8 choose 5, menu 5, 3, 8 choose 5. There's 56 different ways that can happen. Okay, so we don't want to draw out the tree diagram because it's going to be very complicated. So we want to be able to think through that logic. Okay. There are 8 different trials. How many different combinations have 5 successes in those 8 trials? So 5, and we tend to read that as 5 choose 8. I need to choose 5 positions out of the 8 to be, in this case, successes. Okay, so generally speaking then, what we get, and what I've created here from our Bernoulli sequence, is a binomial probability distribution, and it's an example of a discrete probability distribution. So the number of successes in a Bernoulli sequence of n trials is called a binomial random variable, and it has a binomial probability distribution. And we've got the relevant formulas highlighted here. The probability of achieving x successes in n independent trials of a binomial experiment is the probability that x equals x, so we're familiar with this notation from the previous video on discrete random variables. It's going to be n choose x, the number of trials, choose the number of successes you're after. It's going to be p to the power of x, so the probability of success to the power of the number of successes, and 1 minus p to the power of n minus x, so the probability of failure to the power of n minus x, which is going to be the number of failures. NCX is a combination. We can calculate that using n factorial over x factorial times n minus x factorial. I'm not going to go into the combinations in great depth here. It's something you would have studied last year, and we really only need to be able to skirt around the edges of it and don't really need too many formulas here. P is the probability of success. Okay, if we have a discrete random variable, one of the things that we need to develop throughout the probability unit is you will often have your CAS for probability questions. It's not to say there will definitely be probability in the tech free paper, but often you'll have your CAS. And the question becomes, what do I actually need to write down It's really important that you start to practice right from the outset what you would write down in a probability problem. And it's really important that you can formulate it in the correct notation and in the context of what the problem is. So if we have a discrete random variable x, and you might need to define the discrete random variable in the question. Let x be the number of times I observe a 6 when I roll the dice, whatever it might be. Okay. We would then define the distribution using the following notation. So the important stuff that defines the distribution is n. How many trials are you doing? You need that number in order to use these formulas, okay? And the second thing is p. What's the probability of success? Everything else can come from that. So the way we write that, so you're going to need to identify that information when you're answering a probability question. You'll need to extract that from the stated information, which will often be worded. The way we can write that is we can say that x is distributed binomially, so bi for binomial, and then we list the parameters, and the important parameters are n and then p. So we always list the n value first, comma, and then the p value. And in doing that, we're going to state what x is representing, the number of sixes rolled when a fair die is rolled, and then we're going to state that x is distributed binomially. This is the value of n, i.e. how many rolls I'm going to do, and this is the probability of success, which in this case would be, in that example I just stated, would be 1/6, the probability of rolling a 6. Okay, so this is the notation we're going to use to sort of define our distribution. Okay, so what we also want to recall is, so that we can solve some simple problems in a tech-free environment, we want to recall that combinations, which is the NCR, can be found in Pascal's triangle. So Pascal's triangle is a special triangle which has always got ones down the two edges, okay? And then each subsequent row in the triangle is established. We've always got ones on either end, but to get every other number, we then add the two numbers that are diagonally above that. So to get this number down here, for example, we are adding 1 and 3 to get 4. To get this 10 here, we are adding 6 and 4 to get 10. So it's very, very easy, quick and easy to generate the first few rows of Pascal's triangle yourself, which means it's very, very easy to use the triangle to calculate some small values of NCR, okay? So what we see here is the first row of the triangle is called the 0th row. It's always going to be a 1. And that's technically 0 choose 0, which is a pretty meaningless idea. Okay, if you've got 0 objects, how many ways can you choose none of them? You know, that's potentially, it's a bit like, you know, dividing by 0 and all those sorts of things that have to be defined mathematically. Then we get the first row. So we have 1 choose 0. So if we have one object, how many ways can we choose none of them? There's exactly one way to do that. If we have one object, how many ways can we choose one of them? There's one way to do that. The next row is the second row. Okay. So if I have two objects, how many ways can I choose none? Well, there's one way to do that. I just choose none. If I've got two objects, how many ways can I choose one of them? There's two different ways. I could choose the first object or the second object. If I've got two objects, how many ways can I choose both of them? There's only one way to do that. Okay. And so each of these rows gives us the value of, so if we want, you know, 5 choose 4, we're going to need to go to the, draw our triangle down to the 5th row, and then that'll be 5 choose, so the first number will be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4. Okay, and so we can find that it's 5 without the need for a CAS. You can also use the formula that I gave you on the previous page if you're comfortable with the factorials. Thinking about Pascal's triangle, though, also allows us to make some observations about NCR. Okay, and the first is these two things, which are sort of the same. Anything choose 0, if we look at the left diagonal, anything choose 0 is always 1. We also know from the right diagonal that anything choose itself. 0 choose 0, 1 choose 1, 2 choose 2, 3 choose 3, 4 choose 4, n choose n is also always 1. If we then look at the next row in, anything choose 1 is always going to be equal to itself. So 1 choose 1 is 1, 2 choose 1 is 2, 3 choose 1 is 3, 4 choose 1 is 4, so n choose 1 is n. If you have n objects and you want to select one of them, there are n ways of doing that. You could choose each of the n objects. The other, the diagonal going the other way, just one row in from the edge, is also giving us some key patterns. So anything, 1 choose 0 is 1, 2 choose 1 is 2, 3 choose 2 is 3, 4 choose 3 is 4, okay? And so we're seeing if I've got 4 objects and I want to select 3 of them, that's always going to be equal to 4. So if I've got n objects and I want to select one less than n of those, that's going to be equal to n. And that's because that's essentially the same question. You've got this symmetry in the triangle that's helpful as well. These two are the same because they're essentially the same question. If you have 4 things and you want to select 3 of them, you want to work out how many different ways you could select 3 of them, the same question is to ask how many different ways can I choose the one object that I won't select. And so that's why we get this symmetry in the triangle, and the symmetry is also important. Okay, so for example, we can see here that these are the same. If I want to choose 2 objects from 6 objects, that's going to be the same number of ways as choosing 4 objects from the 6 objects. Because if you're choosing 2 objects, you're at the same time choosing to leave 4 objects behind. So we get this symmetry. So NCR is going to be the same as NC n minus R. Okay, so 20 choose 18 would be the same as 20 choose 2. Okay, so we've got that symmetry happening. Okay, so these patterns, being able to generate the triangle and making use of these patterns allows us to calculate and evaluate some of the smaller combinations without the use of a calculator. However, if we do have a calculator, as we've already seen, menu 5.3 enables us to work out NCR. Right, let's work through some examples. A fair die is rolled 5 times and the number of 6s that occur is noted. Find the probability of rolling exactly 1 6, rolling more than 3 6s, etc. Let's define the problem first. Okay, so I need to introduce a variable. You can use any letter. I'm going to use x, but it doesn't need to be x every time. Capital letter. So x is going to be the number of 6s that I roll. Number of 6s rolled. X is a binomial random variable, and that's because this follows a Bernoulli sequence. Each roll, I can either roll a 6 or not roll a 6. So 2 outcomes at each stage. The probability of rolling a 6 doesn't change. It's the same for every trial. Okay, and each of the trials are independent. Whether or not I roll a 6 at one stage doesn't affect the probability I'll roll a 6 at the next stage. So that it creates a Bernoulli sequence, and therefore the probability distribution will be a binomial probability distribution. So x is distributed binomially, and then we need to give n and p. Now in this case we're rolling the dice 5 times, so n will be 5. P is the probability of success, and we're interested in rolling a 6, so p is 1/6. So that is defining our problem here, and it's really important that we get in the habit of doing that. Okay, so find the probability of rolling exactly 1/6. So we want the probability that x is equal to 1. Okay, x being the number of 6s rolled is equal to 1. Okay, so we have to find x before we can make this statement. So it's really important. What you write down is really important here. Okay, probability of rolling exactly 1/6. Now we can go back to our formula up here on the previous page. So what we're going to have is NCX. So in this case, 5 choose 1. So that's the number of ways I can roll, number of different ways I can roll 1/6 out of 5 rolls. Okay, multiplied by the probability of success, which is 1/6, to the power of the number of successes, which in this case is 1, and then also multiplied by the number of the probability of failure, which is 5/6, that's 1 minus 1/6, to the power of the number of failures. So if I'm going to have 5 rolls, 1 of them has to be a success, 4 of them therefore have to be failures. Okay, so remember this is n minus x, 5 minus 1, so that's 4. And then we want to work that out. Okay, so if I think about my combinations, I know that 5 choose 1 is 5. Okay, 1/6 to the power of 1 is still 1/6. 5/6 to the power of 4. 5 to the power of 4 is, sorry, I may as well just do the whole thing. 5/6 to the power of 4 is 625 on 1296. Okay, so we can use our calculator to work it out. And I could have just typed the whole thing in the calculator from the start, but I just want to be clear about, we know what that equals. We can simplify that. I'm going to power of 4, 6 to the power of 4 and 5 to the power of 4. I can certainly work them out, but they're not at the forefront of my memory. Okay, so 5 times 1/6, so that's 5/6, and then times 625, oops, sorry, 625 on, sorry, I'm going to do that again, 625 on 1296. And we get 3125 on 7776. Sorry, 7776. is the probability of rolling exactly 1/6. If you want to see what that is as a decimal, fine. Okay, it's about 0.4. Yes, that makes sense to me. But if you're not told to give a rounded answer, you would give it exactly. Okay, part B, find the probability of rolling more than 3 sixes. Okay, so probability that x is bigger than 3. Again, be clear about the difference between bigger than or equal to versus bigger than, and make sure you're using those correctly. So more than 3 sixes means we could either roll 4 sixes, or we could roll 5 sixes, or we could roll 6 sixes. Okay, so probability that x equals 4 is going to be 5 choose 4, then it's going to be 1/6 to the power of 4, 4 successes, and we'll have 1 failure, 5/6 to the power of 1. Okay. Oh, sorry, there's not going to be x equals 6. We're only rolling the die 5 times. So we can have more than 3 sixes. When we roll it 5 times, we can either have 4 sixes or 5 sixes. And then the probability that x equals 5 is going to be 5 choose 5, which is 1, times 1/6 to the power of 5, and times 5/6 to the power of 0, which is 1. So it's really only this. Okay. All right, so we can type that into our calculator. 5 choose 4, if we want to do a bit of simplifying ourselves, 5 choose 4 is the same as 5 choose 1, which is 5. And then this is times 1/6 to the power of 4 and times 5/6. And then this is just 1/6 to the power of 5, because that's 1 and that's 1. Okay, let's work it out. 5 times 1/6 to the power of 4, times 5/6 plus 1/6 to the power of 5. And that is, let me just check I've typed that in correctly, 1/6 to the power of 5, 1/6 to the power of 4. Yep. And that is going to be 13 on 3888. Okay, probability of rolling 4 sixes or less. So probability that x is less than or equal to 4. Okay, so we can either do probability that x equals 0 plus probability that x equals 1 plus all the way up to probability that x equals 4, but that's going to require us to calculate 5 different probabilities and add them all up. So the quicker way to think about this is, well, this is the same as, if we want to roll 4 or fewer sixes, that's the same as calculating 1 minus the probability that I roll 5 sixes. Okay, so thinking about how you can use the sort of complement to enable you to use a simpler calculation. So it's 1 minus, this would be 5 choose 5, 1/6 to the power of 5, times 5/6 to the power of 0. Again, this is 1, this is also 1, and so it's really just 1 minus 1/6 to the power of 5. So 1 minus 1/6, sorry, I should put a bracket there, so I can put my power here, 1/6 to the power of 5, and so it is 7775 on 7776. Probability of the first roll being a 6 and the rest not. Okay, so this is really important. This is not the same as probability that x equals 1. This isn't asking you, this isn't saying find the probability that you roll 1/6. Okay, because rolling 1/6, the binomial distribution would work out the probability of the first roll being a 6 and the rest not, the probability of the second roll being a 6, plus the probability of the second roll being a 6 and the rest not, plus the probability of the third roll being a 6 and the rest not. So we're not interested in this. Okay, we're actually only interested in one specific branch of this tree diagram. So this is the probability that we get a 6 and then not, and then not, and then not, and then not. So we can just work that out. That's just thinking through that single branch of the tree diagram. So the probability of getting a 6 on the first roll will be 1/6, then not a 6th is 5/6, not a 6th, not a 6th, not a 6th. So it's just 1/6 times 5/6 to the power of 4. We don't have 5 choose 1 out the front here because we're not interested in the 5 different positions that the 1/6 could be in. We only want the one branch where the first roll is a 6 and then the next 4 rolls are not 6s. Okay, so we can calculate this. 1 divided by, so 1/6 multiplied by 5/6 to the power of 4. and that is 625 on 7776. So this is where I really want you to be careful about, being clear about what's actually being asked. Is this working out a binomial probability, or am I just needing to think through one particular branch in the tree diagram? I'm not going to draw the whole tree diagram. I'm doing 5 rows. That would be, a big tree diagram, but I want to be able to think through what one particular branch that I'm interested in would look like. Okay, let's have a look at another example. A full forward has a probability of 0.35 of kicking a goal from a free kick. In a particular match, he has 8 free kicks for goal. Find, correct to 4 decimal places, the probability that. Okay, so the first thing I need to do is set up my problem. Okay, so let's not use X just to show that we can use something else. Let's say G is, so in a binomial distribution, it's a discrete distribution. It will always be the number of something. Okay, try to formulate it in that way in your head. G is the number of what? Okay, so in this case, what we're interested in is the number of goals kicked. Technically from free kicks, but we don't need to be super precise. Let's just be clear about what's happening here. So number of goals kicked is what I'm interested in. Okay, yes, we can say from free kicks. But number of goals kicked would probably be sufficient there. Now, G is a binomial distribution because we have a sequence of Bernoulli trials here. Now, this is a slightly simplified version. Realistically, it's probably not exactly a binomial probability, but for the purposes of the calculation and the information we've got, it is. So, binomial, there's success or failure at each trial. So each trial is taking a free kick at goal, and he can either kick the goal or not kick the goal. There's the 2 trials. The second condition is that the probability of success has to be the same at every attempt. And this is where this is a simplified version of real life, because realistically he's not going to have exactly the same probability at every kick. He'll be in different positions, he'll be more tired from having run faster or further, or whatever it might be. But for this problem, this full forward has a probability of 0.35 of kicking a goal from a free kick. So we're assuming that that is the same probability every time. And then the third condition is that the probabilities are independent. And again, this is probably slightly possibly not true, but we don't have the information to be able to infer that. So independence meaning that the probability of him kicking a goal at the next free kick is not being in any way affected by him whether or not he kicked the goal at the last free kick. And realistically, there's possibly some sort of mental game happening there if he's missed the last few kicks that might be having an impact as well. However, for the purposes of this calculation, we don't have all that information, and so we're going to simplify this to be a binomial situation. So the first thing we need to list is n, which is the number of trials. So in this case, that's the number of free kicks. So in this case, he's got 8 free kicks for goal. And then p, the probability of success, the probability that he kicks the goal from the free kick, we know is 0.35. Okay, so that's our setup. Now we don't need to repeat that for any subsequent parts. Once we've set that up in the first part of the problem, we can understand that that can follow through. So you would find, for example, in an exam, something or a test, something like this would be worth 2 marks here, and then it might be 1 mark for the rest of them, because we're going to do the setup in part A, but we don't need to repeat it again in parts B and C. Okay, so part A, we want the probability that he kicks 2 goals. So probability that in this case G, the number of goals kicked from free kicks, is 2. Okay, and then we know it's going to be NCX, so that's 8C2 times the probability of success, which in this case is 0.35 to the power of 2, the number of successes, the number of goals kicked, and then times the probability of failure, 1 minus 0.35 is 0.65, and obviously if he had 2 successes he has to have 6 failures. And so then we can work that out. So menu 5, 3, 8, choose 2, multiplied by 0.35 to the power of 2, and multiplied by 0.65 to the power of 6. Okay, my question specifies correct to 4 decimal places, so only giving rounded values if the question instructs me to, but in this case it does, and I must give it to 4 decimal places or else it won't be correct. So 0.258, and rounding correctly I need to round up, so 87. Probability that he kicks no goals. So this is the probability that G, the number of goals kicked is 0. So that is going to be 8 choose 0, 0.35 to the power of 0, 0.65 to the power of 6. Okay, so essentially that's 1 and that's 1, so we've really just got that. And that's because there's only going to be, if we were to imagine this tree diagram, one branch in the tree diagram where he kicks no goals, and that is the branch where he misses 8 times. Sorry, that should be 8. He misses 8 times, so it's just the probability of failure to the power of 8. 0.65 to the power of 8, and that's because 8 choose 0 is 1, and 0.35 to the power of 0 is also 1. So 4 decimal places, 0.0319, correctly rounded. Probability that he kicks at least one goal. So probability that the number of goals kicked is at least 1. Okay, again, thinking about, well, that would be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 goals. Or we could do 1 minus the probability that he doesn't kick any goals, which we've already worked out. Sorry, 0.0319. Again, don't use your rounded answers in your calculation. There's no reason to in the CAS. You've got your exact answer here. Okay, always being cautious about using rounded answers in subsequent calculations. Okay, part D, the probability that he kicks 2 goals given that he kicks at least 1 goal. So we've got a conditional probability here. Probability that the number of goals kicked is at least 2, so greater than or equal to 2, given that the number of goals kicked is at least 1. Okay, so we're going to want, thinking about our conditional probability, we need the intersection of those two things over the second thing. Okay, so probability that he kicks at least 2 goals given that, probability of kicking at least 2 goals and at least 1 goal, the intersection of those two things, okay? At least 2 goals means he kicks 2, 3, 4, 5, or 6 or 7 or 8 goals. At least 1 goal means he kicks 1, 2, 3, 4, 5, 6. So the overlap, the intersection, is kicking at least 2 goals. Okay, so that is probability that he gets at least 2 goals over the probability that he gets at least 1 goal. Okay, so let's think about at least 2 goals. I'm just going to do that separately out here. So probability that he gets at least 2 goals is the same as 1 minus the probability that he gets no goals minus the probability that he gets 1 goal. Okay, so we already know that's 0.0319. Have we worked out 1 goal? No, we haven't. We've got at least 1 goal. Okay, so probability of 1 goal, I can work that out. That would be menu 5.3. It's going to be 8 choose 1 times 0.35 to the power of 1. Oops, power of 1. Let's try that again. Power of 1 times 0.65 to the power of 7. So 1 success, 7 failures. In 8 choose 1 different ways of doing that. So 0.1373. Okay, again, I'm not going to use rounded values. I'm going to do 1 minus this nice exact answer up here minus this answer here, which is 0.8309. Okay, so that is the probability of getting at least 2 goals. Okay, so it's 0.8309 over the probability of getting at least 1 goal, which we calculated in the previous part, which was 0.9681. We want our final answer correct to 4 decimal places, so I'm not going to use my rounded 4 decimal place answers to calculate another answer to 4 decimal places. So I'm going to take them exactly in my CAS. So I want that number there divided by this number up here. And that correct to 4 decimal places is 0.8582. Okay, I also want to introduce the idea of expectation and variance for a binomially distributed variable. So here we have our probability distributions. I'm going back to the original example we looked at, where we've got a binomial random variable, 3 independent Bernoulli trials, each with a probability of success of p, and the probability distribution is given by this. We generated that ourselves earlier. Okay, so we remember that in the previous video we looked at how we calculate expected value, and we do that by adding up, by calculating each x value, multiplying by its probability. Okay, multiply 1 by 3p times 1 minus p squared, x value times probability, x value times probability, and then we add those up. Okay, so that's what we've got happening here. Each x value times its probability being added up. And if we simplify and tidy that up, we find that in this particular case, the expected value of x would be 3 times p. Okay, and in this particular, and this is not precisely a proof, we're making some assumptions here, but remember that this was a situation where we had 3 trials, and we're seeing that the expected value is 3 times the probability of success, and actually we can generalize that to say that if we had n trials, the expected value would be n times the probability of success. And that makes sense. Like if you think about the footballer in the previous example, if he's got a 0.35 chance of success and he's going to have 10 shots, we would expect him to kick 10 times 0.35 or 3.5. Obviously we can't, if it was goals, it wouldn't be a decimal, but we would expect him to kick 3.5 goals. Let's say he takes 100 shots. We would expect him to kick 35 of those goals if that's his probability of success. Okay, so it's quite intuitive as well. Expected value for a binomial distribution will be n times p. And then we recall that for a discrete random variable, we use this formula to find the variance, expected value of x squared, which is what's being calculated. Oh, sorry, there's a squared missing there. Can you add that in? Which is what's being calculated in this first line. So we do our x value squared times by its probability, x value squared times by the probability, x value squared times by the probability. And if we tidy all that up and work it through, you can follow it, pause and follow it through yourself. We find the expected value of x squared is this. And then we also need the expected value of x squared, which is that, minus the expected value of x all squared, which is that. Okay. And again, we tidy all this up, simplify it, and we get here. And we find that the variance of x is 3, which was n, times p times 1 minus p. And we can generalize that for any binomial probability distribution. The variance of that distribution is n times p times 1 minus p. So the number of trials times the probability of success, and then times the probability of failure. And obviously we can also then calculate standard deviation by taking the square root of the variance. So we've got those 3 things summarized here. So mean, we can either call it mu, which we tend to use more for continuous distributions, or expected value of x is np. Variance, which is either sigma squared, which we tend to use a bit more for continuous distributions, or we can write it as variance of x, is n times p times 1 minus p. And the standard deviation, which is sigma, or SD of x, is the square root of the variance, and so the square root of n times p times 1 minus p. Okay, so let's just have a look at using those. A company produced party balloons and packages them in lots of 10. If 20% of the balloons produced are yellow, find. Okay, so let's have y is the number of yellow balloons in a packet. Yellow balloons per packet. Y is a binomially distributed variable. The balloon is either yellow or not yellow, and 20% of all the balloons produced are yellow, so the probability of a balloon being yellow is 20%. So in this case here, and that doesn't change, in this case here we've got n is 10. They're packed in lots of 10. Okay, so n is 10, and the probability of success, the probability of a balloon being yellow is 20%, because all balloons, 20% of all balloons that are manufactured are yellow. Okay, so that's our setup. We want the expected number of yellow balloons per packet, so expected value of y, which is the number of yellow balloons per packet, is going to be n times p, so in this case that is 10 times 0.2, and so we would expect 2 balloons per packet to be yellow. As I said, that's really intuitive, okay? If 20% of all balloons are yellow balloons and you've got 10, how many would you expect to be yellow? 20% of them. Variance of the number of yellow balloons per packet. So we're going to need variance of y, which we know is n times p times 1 minus p, so that's 10 times 0.2 and times 1 minus p, which is 0.8. So that's going to be 2 times 0.8, which is 1.6. Now variance doesn't need to be to the nearest whole number, it's talking about the spread, just because we're dealing in balloons and you can't have 1.6 of a balloon, we wouldn't round that. In the same way we wouldn't have rounded the expected value either if that hadn't been a whole number. Variance, remember, actually also isn't even in the units of balloons. It's actually 1.6 balloons squared, so it's completely meaningless, the units, and so we wouldn't write them. Okay, one more example. A biased die is rolled 12 times. If x represents the number of 3s that occur and the expected value of x is 10, find p. Okay, so biased die is rolled 12 times. It's a binomial distribution. X is the number of threes, okay? So that's already, the sentence is already written for us. X is already defined, so we don't need to write out the sentence, but we do know it's binomially distributed. We're rolling the die 12 times, so n is 12, and it's a, it's a biased die. We don't know what p is, that's the point. So if it was a fair die, p would be 1/6, rolling a 3, but it's a biased die, so therefore we don't know what p is. P is what we're trying to find in part A. What we do know is the expected value of x is 10. So we know that the expected value of x would be n times p, and in this case that is going to be 12 times p, and we know that has to equal 10. And so therefore p is 10 on 12, which is 5/6. And then we want to work out the standard deviation of x. So before we can work out the standard deviation, we work out the variance, and then it will be the square root of that. So it's the square root of the variance of x, which means it's the square root of n times p times 1 minus p. And we now have all those values. N we have from the question, it's 12. P we've just worked out is 5/6, and therefore 1 minus p is 1/6. And so we can work that out. It should, no, we'll leave that as it is. So we're going to have 12 times, actually let's just work it out, sorry. Square root of 12 times 5, my apologies, 12 times 5/6 times 1/6. And it doesn't tell us to give a rounded value, so we'll leave it as root 15 on 3. If it asked for that to 2 decimal places, Control Enter 1.29. But it doesn't specify that in the question, and so therefore we're going to leave our answer exactly. Finally here, I'm going to link to another video just for a bit of fun, and I'm going to just have a quick look at some questions from that. I'll link it here on YouTube that you can click on it. It's about a 6-minute video, and it's a probability experiment where he's trying to roll a 1-roll Yahtzee. So he's got 5 dice, and he's trying to, in one roll all 5 numbers the same. Okay. The first thing to talk about is in the video, he talks about the fact that the probability of rolling a 1-roll Yahtzee is 1 in 1296. Okay, so this is the probability that if he rolls 5 dice, all 5 of them will be the same. Okay, and let's just have a think about calculating that. So you might think that's not quite right, because you might think, well, it should be 1/6 times 1/6 times 1/6 times 1/6 times 1/6, and that's not 1 on 296, because 6 to the power of 5 is 7776. That would be 1 on 7776. But that's actually not correct. The 1 on 1296 is correct, and that's because this first one isn't 1/6. The first one is 1. The first roll, you can roll anything. Doesn't matter. Doesn't matter whether you roll a 1, 2, 3, 4, 5, or 6 in the first roll, but then the next roll after that has to match. So there's only a 1/6 probability that it will match, or the next dice, sorry. The third dice has to match as well, so also a 1/6 probability that it will match. Again, 4th and 5th die also have to match the original first die. So it's actually only 1/6. Sorry. It's actually only 1/6 to the power of 4. Power of 4, which is 1 on 1296. Okay, so that's the probability that on any given roll, when I roll all 5 dice, that I will get a Yahtzee. That is that all, if you're familiar with the famous game Yahtzee, that is that all 5 dice show the same number. Okay, so in the video he claims that the probability of rolling a 1-roll Yahtzee is 1 on 1296. That's true. But the probability of actually rolling a Yahtzee in 1296 rolls is around 63%. That stat that he quotes in the video, that can actually be calculated using a binomial probability distribution. Okay, so if we have x is the number of 1-roll Yahtzees, sorry, try and spell it right, 1-roll Yahtzees, okay, we're saying x is a binomial distribution. We want to know what's the probability that he will actually roll a Yahtzee if he does 1296 rolls. So n, the number of rolls, is going to be 1296, and we know the probability that any one of those rolls is a Yahtzee would be 1 on 1296. Okay, so we want to know the probability that if we were to roll the dice 1,296 times, that we would actually get a Yahtzee. So it's not just the probability that x equals 1, okay, because then we wouldn't roll the dice 1,296 times, we would just stop. So we want to know the probability that in 1,296 rolls, we get at least one Yahtzee. So that is 1 minus the probability that we get no Yahtzees. So that is 1 minus 1296, choose 0, times 1 on 1296 to the power of 0 times 1295 on 1296 to the power of 1296. Okay, so if we calculate that, that is going to be 1 minus, that's 1, so we're just really working out this bit, so it's just 1 minus 1295 on 1296 to the power of 1296. Let's calculate that as a decimal. So 1 minus 1295, 1295 on 1296, and we want that to the power of 1296. And we find that that is approximately 0.63, which is the 63% he found. So if he was to actually, whilst the probability of, on any given roll, the probability of getting a Yahtzee is 1 on 1296, that doesn't mean that if you were to roll the dice 1,296 times that he would be assured of getting a Yahtzee. There's a 63% chance that if he were to roll it that many times, he would get a Yahtzee. Later in the video, Brady claims that if he rolls the dice 2,920 times, he has a 90% chance of obtaining a Yahtzee. Okay, so again, this time, same probability, x is still defined the same. The binomial distribution changes slightly because we're now doing 2,920 rolls, but the probability of a Yahtzee at any given roll stays the same. We again want the probability that x is bigger than or equal to 1, but in 2,920 rolls. So it's going to be 1 minus the probability that x equals 0. So 1 minus, in this case, it'll be, 2920, choose 0, which is 1. Probability of success, which is 1 on 1296 to the power of 0, which is also 1. And so 1295 on 1296 to the power of 2920. So it's really just 1 minus 1295 on 1296 to the power of 2920. So I can get my CAS to work that out. We should be around 90%. Let me just edit my previous calculation here, making this power instead 2920. Yep, to 2 decimal places, yes, that will be 0.90. And so about 90% chance that if you were to roll the dice 2,920 times, you should get a Yahtzee. Obviously still a 10% chance that you don't, and you would need to roll the dice further. Okay, so that's the binomial distribution. The work today is a mixture of questions from 14A and 14B. In the next video, we'll have a look at further binomial probability problems where we make use of the inbuilt binomial distribution functions in the CAS to calculate more complicated probabilities.